Alright guys, here we go. So I'm going to try and cover as best as I can the stuff that we missed in class. Again, I apologize that we ran out of time, but hopefully this will clear some of the things up, get everybody back on the same page. And I want to start going over the contour lines again because that's kind of where we left off. But I just want to make sure everybody's clear on that, even if it might be a little bit of a recap for you if you went over this stuff in your basic map reading class last year. I still want to make sure that everybody is on the same page with the contour lines. So especially it's going to help you out tomorrow with lab and with the actual land nav class that we'll do next week. So anyway, here we go. So contour lines are the most common method of showing relief and elevation on a standard topographic map. So a contour line represents an imaginary line. It's obviously not really drawn on the ground, but it's an imaginary line on the ground that's either above or below sea level. And all points on the contour line are at the same elevation. So if you follow the contour line all around the map, wherever it goes, this line is always going to be the same elevation wherever that line goes until it ends or until it circles back on itself. The elevation represented by contour lines is the vertical distance above or below sea level. So for example, this one is 400 meters above sea level. The three types of contour lines used on the standard topographic map are the index, and the intermediate, and your supplementary. So index, starting at zero elevation or mean sea level, every fifth contour line is a heavier line. So if you look on a regular map, and if I'll send you guys the PDF of the map of the Fort Knox map, miniature version of what I gave you guys, the big ones in class today. But you'll see every 50 meters is a thick boulder line. So the next one up from here would be 450, the next one down would be 350, and so on. And it's every fifth line is a heavier line. So these are known as the index contour lines. Normally each index contour line is numbered at some point. And this number is the elevation of that line. So again, this actual contour line is at 400 meters above sea level. Intermediate contour lines fall between index contour lines, and these lines are finer. They don't have the elevations given, but there are normally four intermediate contour lines between index contour lines. So see this little bold line here in the corner. Go down from this, be 400 meters, then down to 390, 380, 370, 360, and then you got your 350 right here. So that just represents stepping down or stepping back up from those baseline contour lines. Supplementary contour lines resemble dashes. You have these little dash marks, and these aren't as common on maps. You will still find them, but they show changes in elevation of at least 1/2 the contour interval. Supplementary lines are normally found where there's very little change in elevation, such as on fairly level terrain, valleys and big plains and stuff like that, where there might be just a very, very gradual change in elevation. You'll see it sometimes on the map, on the bottom of the map, it'll show you your interval for the normal lines, which is on 10 meters on the Fort Knox map. And then also below that will say supplementary contour intervals is 5 meters. So again, it's just a very gradual change in elevation. All right, so let's go on and talk about the protractor again. If you have your protractor with you, great. If you don't, it's fine. Just reference the screen here. But I want to go over it one more time just to make sure that you guys are straight on how to use this, because this is an incredibly important tool. It is essential to properly being able to plot your grids, plot your azimuth, plot your points, excuse me. So you're going to need to know exactly how to use this, because if you use this improperly, you're going to be totally lost in the sauce. So know how to use this properly. So the protractor is what's called a U.S. Army Graphic Training Aid, or GTA 5-2-12. But there's four major components of the protractor. So the first is the crosshair in the middle, that's used as a vertical and horizontal reference to the north and south and east-west grid lines on your military grid map. So those are right here for your north and south, and right here for your east and west. Okay. Then this cross right here is called the index. That's your index line where those crosshairs meet. The three scales on here are your 1 in 100,000 meters, your 1 in 50,000 meters, and your 1 in 25,000, or sometimes you'll see 1 in 250,000 meters. The scale is used with the corresponding scaled map. So the ones that you used in class and the ones that are most commonly used are 1 in 50,000, these ones right here in the upper left-hand corner. Make sure that you know exactly what the scale of your map is, because if you use the wrong triangle for the wrong scaled map, you will be lost. You will be inaccurate, and you will not be able to find your way at all. The inner scale, we talked about this, but I want to go over it again. The inner scale depicts your 360 degrees and is used to determine or plot your azimuths. So this scale determines the grid azimuth compared to the magnetic azimuths that are given by your compass. So you always want to focus on these lines here. This is exact same 360 degrees that you'd see on your compass. This is just in grid form, in a quadrangular form that accommodates using it on a grid map instead of using it on a round compass. The outer scale depicts your mils. There are 6,400 mils in a circle. So 6,400 mils in 360 degrees. And the mil scale is used primarily for indirect fire purposes, because indirect fire assets prefer to compute fire support using mils because it's more accurate than degrees. But it sounds like new technology nowadays. You can just punch in a regular grid coordinate and it'll convert it to mils. But still, it's more accurate if you can give some kind of fire support element mils. Anyway, don't worry about that right now. So with that in mind, let's talk about how you determine your grid coordinates. Okay, so what are grid coordinates? The Earth's surface is divided into 6 degrees by 8 degrees quadrangles covered with 100,000 meter squares. So what that means is each portion of the Earth's surface is divided up into 100,000 meters. So the military grid reference of a point consists of the numbers and letters indicating where in that 100,000 meter grid zone areas the point lies, plus the coordinates locating the point to the desired position within the 100,000 meter square. So I'll clarify here in a minute. All right, so there's a cardinal rule of reading grid coordinates, and that is always read right and up. Whenever you're reading your grid coordinates, the first set of numbers that you're going to read are going to be read from the right, and then your second set will be read from up, from bottom to top. And I'll show you here what I mean in a second. So first thing you want to do, again, select that right scale, the proper scale on your protractor, whatever scale, whatever triangle corresponds with the scale of your map. Second you want to do is place the horizontal scale on the grid line with the 0, 0 point. So that means the corner right here on the edge of on the corner of your triangle where the zeros meet, that point is, you want to line that up with the horizontal scale on the grid line at the lower left-hand corner of that grid square, whatever grid square you're going to be operating in. Next, you will slide the scale right, like that way, until the vertical scale intersects the center of your plot point. And then you read right and then up. Okay, so I'll show you here in a second. But you will only ever move your protractor to the right. You will never move it up. You will never move it down. You will never move it to the left. You will only ever start from that 0, 0 point in the lower left-hand corner of that grid square, and then move it to the right to get your number, to get your protractor in the right spot based off of whatever your grid coordinate is. All right, so let's talk about the different kinds of grid coordinates. So you have your basic 4-digit grid coordinate. Okay, a 4-digit grid coordinate is the grid square your grid coordinate is in. And a 4-digit grid coordinate will get you within 1,000 square meters of your plot. So submitting a 4-digit grid coordinate is not very useful, except for quick referencing a key terrain feature or an item on the map. But you want to start from the bottom left-hand corner of the map sheet and read right until you come to the north-south grid line that just precedes your target or your plot. And then you read up until you reach the east-west grid line that just precedes your target point, or your target or your plot. So imagine your squad had to find a food or ammo cache and you were given a 4-digit grid coordinate, it'd be very difficult to find with a degree of accuracy of 1,000 by 1,000 meters. So first off, the first thing you want to do when you are getting your grid coordinate is you want to identify the 100,000 grid square identification letters. So those are these two letters right here. So that tells you that you're going to be in the right section of that map. If that map is broken up into different sections, like say if you're going to have different 100,000 meter grids or squares that meet at some point on that map, you need to look over here at this 100,000 meter square identification and make sure that you are in the right portion of that map that follows with whatever your square identification letters are. So for this case, you'd be in the bottom right-hand corner of this map. Once you've done that, you read right to the last grid before your point. So for this one, the first number 03 is going to be the numbers that you're going to look for down here on the bottom of the map. Okay, so your north-south lines. The first two numbers will always be your north-south lines. And then secondly, you're going to read up until you find your east-west line, your horizontal line, which is the 80 up here. Okay, so you start at the bottom, find the 03, then you go up until you hit that 80. So this box, this grid square, is where you would be operating within from this 03 line reading right and the 80 line reading up. Make sense? Okay. Okay, now let's talk about the 00 marker. So this is what I was talking about. When you have reached the intersection of the north-south grid line and the east-west grid line, that is to the left and below of your target or your point, you are now at the zero mark. So the 0 mark will give you 4 digits, the 2 from your north-south grid line and the 2 from your east-west grid line. So in this, for whatever reason, this is wrong, and it kind of tripped me up, but it should be over here because we were operating in this 0380 box, right? But this is how you would do it. This is how you would line it up. So you line it up not with the crosshairs that are in the middle of the protractor, but you line it up with the lines on the triangle itself, okay? So this little corner right here where the zeros meet is where you would put it. It should be over here. But you would put it in this corner, the bottom left-hand corner of the grid square that you will be operating within to find whatever grid point you're looking for. So as you can see, just finding the 1,000-meter square is not very accurate. If you were searching for that food or ammo crate for your squad and all you had was a 4-digit grid, think how long it would take to check each one of the 1 million little square meters. So this isn't the ideal thing. I say again, this is just kind of a quick reference way to get you in the right general area. But so now let's talk about 6-digit grids. So a 6-digit grid coordinate will get you within 100 by 100 meters of your plot. So this is more accurate than the 4-digit grid you previously plotted, obviously. So say your squad would have better odds of finding the food and ammo cache, and you were given if you were given a 6-digit grid coordinate. However, it would still be very difficult to find it with a degree of accuracy of 100 by 100 meters for obvious reasons. But adding a third number onto each set will get you within that 100 by 100 meter range. So now it's 030806. So you wouldn't move your protractor at all since it's 030. So you're not going anywhere to the right any further than you already were, but you will read slightly further up from the 80 grid. So you'll be within that 600 meters, right? Because this is 1,000 meters from here to here. So this 6 will put you at 600 meters north of that grid line, if that makes sense. Okay, so you're not moving anywhere east, but you are moving a little bit north to 600 meters north. So for this 6-digit grid coordinate, that would be your point right there, right on that line where the 6 meets. Okay, now to go even one step further, there's an 8-digit grid coordinate. An 8-digit grid coordinate will get you within 10 by 10 meters of your plot. So this is more accurate than the 6-digit grid, obviously. And now you and your squad will only have to search an area that is 10 meters by 10 meters, vastly decreasing the time required to find your supplies. So this is the most common grid coordinate you will see, particularly when we're doing land nav and the like. You can even go so far as to doing 10-digit grid coordinates, but we won't commonly see those. But this will get you pretty darn close to where you need to be to find your point that you plotted. And so again, for this one, now it's 0305. So now you will move your protractor slightly to the right to get you in between the 0 and the 1 here. So there's a little hash mark, like you see, there's a little hash mark in between each set of numbers. So that represents 50 meters. Okay, so there's 0 meters, 50 meters, 100 meters, 150, and so on. So this will put you 50 meters slightly to the right, and then you're still going to be up here 8060. So again, you're not moving any further north. You're still just right there on that 6 line. Okay? All right. Now, we're going to move into some slightly more complicated territory, but try and stay with me, and I'm going to try and keep this not too much longer. So let's talk about some of the methods of expressing direction. Okay? Being in the right place at the prescribed time is necessary for successfully accomplishing military missions. Direction plays an important role in a soldier's everyday life, and this learning objective identifies the units of angular measure along with the 3 types of north. So this will further explain how to determine the grid, back, and magnetic azimuths with the use of your protractor, and also use of some field expedient methods to find directions, the conversion of azimuths from grid to magnetic and vice versa, and also we'll talk about some advanced aspects of map reading such as the declination diagram, intersection, resection, and modified resection. So you have 3 different units of angular measure. So you have degrees, mils, and grads, right? So degrees are the most common unit of measure that we'll see. So you'll have degrees with its subdivisions of minutes and seconds if you want to get super detailed on degree directions. Mils, another unit of measure. The mil, abbreviated with an M/, like an M/ in graphics, is used mainly in artillery, tank, and mortar gunnery. The mil expresses the size of an angle formed when a circle is divided into that 6,400 angles, with the vertex of the angles at the center of the circle. And the grad is a metric unit of measure found on some foreign maps. And there are 400 grads in a circle. A 90-degree right angle equals 100 grads. But you will almost never see grads. I've never seen them in my career. So, but then let's talk about the baseline. So 3 different types of north are very important to remember. True north, magnetic north, and grid north. So true north is a line from a point on the Earth's surface to the North Pole. And all lines of longitude are true north lines. True north is usually represented by a star, like you're pointed at the North Star. Magnetic north is the direction to the North Magnetic Pole as indicated by the north-seeking needle of a magnetic instrument like a compass. The magnetic north is usually symbolized by a line ending with half of an arrowhead on your declination diagram, and magnetic readings are obtained with instruments such as the Lensatic and M2 compasses, like we have the little green compasses. But it's been proven that the geomagnetic poles migrate over time, so it's important to always check the most recent updated maps and looking at that declination diagram to see, because it has changed from time to time. It'll change however many degrees you need to subtract or add to convert from grid to magnetic or vice versa. And then lastly, your grid north is established by using the vertical grid lines on the map. Grid north may be symbolized by the letters GN or the letter Y. I don't know why, but it is. But that is your just straight north-south grid lines on your military maps. It's very simple. All right, so let's talk about determining your azimuth. So an azimuth is defined as a horizontal angle measured clockwise from a north baseline. So this north baseline could be true north, magnetic north, or grid north. The azimuth is the most common military method to express direction. So when using an azimuth, the point where the azimuth originates is the center of an imaginary circle. Okay, So this circle is divided into 360 degrees or 6,400 mils. The back azimuth, this is the opposite direction of the azimuth. Like I said, it's comparable to doing an about face. To obtain a back azimuth from an azimuth, you add 180 degrees if the azimuth is 180 degrees or less, and you subtract 180 degrees if the azimuth is 180 degrees or more. We'll talk a little bit more of that with intersection and resection. But the back azimuth of 180 degrees may be stated as 0 degrees or 360 degrees. So it's just important to know that the most common unit of measure is the degree with those minutes and seconds, and that the origin point of an azimuth is the center of that imaginary circle. Okay, so usually when you're using the protractor, you'll use that center line. I'll put my crosshairs over my origin point for point A, and then I'll just draw a line from the middle of the protractor out towards point B, wherever that might be, and that line will take me to where my grid azimuth is. Okay, so let's talk about determining a grid azimuth. So when an azimuth is plotted on a map between point A, your starting point, and point B, your ending point, the points are joined by a straight line. So here you have your point A on this grid coordinate here, and your point B up here. Your protractor is used to measure the angle between grid north and the drawn line, and this measured azimuth is the grid azimuth. So again, you'll usually put your crosshairs of your protractor over this point right here, and then just draw that line with some kind of straight edge. Doesn't matter what it is, piece of paper, whatever you can find. Some people use a string. And you just draw that line out to point B, whatever the other point is that you've plotted. And then when you place your protractor on top of your origin point with your crosshairs lined up parallel with the north-south lines and your east-west lines, then wherever that line takes you to will give you your grid azimuth, like so. So they drew this line out to here, and they came up with 57 degrees from your origin point to point B. Okay? So that is your grid azimuth. All right. Now let's talk about the declination diagram. The declination diagram is so important. Okay? I can't stress this enough. You have to be able to determine how many degrees you need to add or subtract depending on whether you're converting from grid to magnetic or vice versa. And not every map is going to be the same. Every map is going to have a different amount of degrees that you need to add or subtract. And sometimes your magnetic north will be on the left of your grid north, and sometimes it'll be on the right of the grid north. It just depends on where you are. On Fort Sill, it's over here in Oklahoma. For whatever reason, the Earth's magnetic field affects compasses differently in Oklahoma than it does in Fort Knox when it's on this side. So you have to pay attention to this in detail because it will greatly affect how you navigate in the real world after you've plotted your points on a map. Okay? All right, so let's talk a little bit about what we're going to discuss here. So we're going to go a little bit more in detail about declination conversion, and then we're going to talk about intersection and resection and the modified resection. I know I talked a little bit about it in class, but I want to go over it in slightly more detail just so you guys are clear on it. But so here, going a little bit more in detail about the declination conversion, you'll see over here on the left-hand side. So this is an example of where to convert a magnetic azimuth to grid azimuth, you subtract the GM angle. So say your 49 degrees is your magnetic azimuth. You subtract, for this example, it's 21 degrees. So you have a 28 degree grid azimuth. So say you're shooting an azimuth with your compass to, let's say, a water tower, and you get 49 degrees on your compass. Then you would have to, in order to be able to plot that point, or plot your azimuth from your location to that water tower on your map, you'd have to subtract those 21 degrees before you could properly plot it on your map to get that 28 degree grid. And then again, in reverse, you would add to go from grid to magnetic, you'd add that 21 degrees. So 28 degrees grid plus 21 degrees for the declination conversion equals 49 degrees magnetic. Okay? And then over here on this side, it's the opposite. So to convert a magnetic azimuth to grid azimuth, you'd add the GM angle, and then, again, reverse for that. To go from grid azimuth to magnetic azimuth, you subtract. Okay? So I know I'm hitting this over the head a lot, but you have to know that when you convert azimuths, you have to exercise extreme care when adding and subtracting the GM angle, because a simple mistake of 1 degree could be significant in the field. So always pay attention to your declination diagram and the conversions. All right, let's talk briefly about intersection. So intersection is the location of an unknown point by successively occupying at least 2, preferably 3, because that'll give you an even more accurate result, known positions on the ground, and then map sighting on the unknown location. So it's used to locate distant or inaccessible points or objects such as enemy targets and danger areas. And there are 2 methods of intersection: the map and compass method, and the straight edge when the compass is unavailable. So the easiest way to do it is using a compass. So I say you have your point where you are, and say point B where your buddy is, where just in any case you have 2 known points. You shoot the azimuth from that point to your unknown location. So say there's an enemy located in this position. So you shoot your azimuth, your magnetic azimuth comes up with 55 degrees. Now again, you have to compensate for that declination conversion. In this case, you add 21 degrees to get your 76 degree grid azimuth. Okay, so now you know to draw from your point, point A, on a 76 degree grid angle out this way. Okay, so that's just step 1. Then step 2, your buddy shoots an azimuth from their position to the unknown point. They get 24 degree magnetic azimuth plus 21 degrees for the declination conversion equals 45 degree grid azimuth. Again, draw a point from draw a line from their point up to the unknown point, and wherever those lines intersect, that is where that unknown location is, that unknown target is. Sorry about that, I had a phone call. Anyway, so that was your regular intersection method using the compass. So this is intersection with a straight edge without a compass. So this is a little interesting, not very commonly used, obviously, because we almost always have a compass with us. But if you are without a compass, this is one way to try and find the location of an unknown object or an unknown target. So basically what you do is first you orient the map on a flat surface by the terrain association method, right? So you actually physically move the map until it lines up with how you are physically standing. And then you locate and mark your position on the map, okay? So right here. So what you do is then you lay a straight edge on the map with one end at the user's position. So say you're using a ruler, right? So one end will be pointing towards you, right here, like physically at you. And then that is used as a pivot point. Then you rotate the straight edge until the unknown point is sighted along the edge. So say right here, looks like an intersection of a road is your point A that you're trying to figure out. So you will have the other end of that straight edge pointing directly at that unknown point. And then basically you're going to draw a line along that straight edge. So that should give you an idea of where that object is, or that target is on the map, by drawing that straight edge and using that terrain association, excuse me. So then you can repeat those steps for positions B or C, or however many positions you need to do to check for your accuracy. And so then the intersection of those lines on the map is the location of the unknown point. Okay? I know that one's a little bit confusing. I say again, we don't use that one very much, so I wouldn't worry yourself too much about it, but it's just interesting to know about it. All right. Now, talking about resection. Resection is the opposite of intersection. It's the method of locating your position on a map by determining the grid azimuth to at least 2 well-defined locations that you can pinpoint on the map. And for greater accuracy, the desired method of resection is to use 3 or more well-defined locations. But for this instance, you will just use 2. So you have 2 known points for this. You have the hill over here, you have the lookout tower over here. So what you're going to do is shoot a magnetic azimuth from your position to those known points. So for the hill, you got a magnetic azimuth of 299 degrees. So now to get your grid azimuth, you're going to have to do that conversion. Again, pay attention to this. And in order to convert from magnetic to grid, you subtract 19 degrees. So 299 minus 19 degrees, and you get 280 degrees. Now, you're not done yet. Now, to get your back azimuth, you have to subtract 180 degrees. Since we are at a greater than 180 degrees azimuth, subtract 180 degrees, and you'll get 100 degrees. So what that means is the azimuth from this known point, from this hill to your location, is 100 degrees grid azimuth. So then you take your protractor, line it up, draw the line 100 degrees out as far as you need to go so to give it enough room to intersect with the other line. So now with the other area, the lookout tower, you shoot an azimuth to that, you get 29 degrees. Grid azimuth, 29 degrees minus 19 degrees is 10 degrees. Now to get the back azimuth for 10 degrees, you're going to add because you're less than 180 degrees. So you add 180 degrees and you get 190 degrees as the azimuth from the lookout tower to your location. And again, put your protractor down, draw the line. There you go, voila. Where those lines intersect, that is your location. So now you can probably plot a point with your protractor to give yourself your grid location, and also just gives you a general idea of where you are on the map, and it allows you to better use your terrain association so you're more familiar with the area. Alright, last thing we're going to talk about, I promise, and then we're done. So just real briefly, we'll talk about modified resection. So modified resection is the method of locating your position on the map when you're located on a linear feature on the ground, like a road or a canal or a stream. And basically, it's still kind of the same concept where you're going to shoot an azimuth to a known point. Like for here, they show a tower. So you're standing, say, along this creek, and you'll shoot an azimuth to the tower. For this, they give you a magnetic azimuth of 158 degrees. Then minus 4 degrees for the declination conversion. You get 154 degrees grid, plus the 180 degrees. So you got a 334 degree grid back azimuth. So if you're along a creek or a road or something like that, it's a little bit easier to do it this way because you have a better point of reference along some kind of a linear feature than you would if you're just in the middle of the woods or on a hill or something like that. So it's a faster way to do it. It may not be 100% within 1 meter accuracy, but it will get you close enough to take care of what you need to do. All right, so that pretty much sums it up. I'm sorry this took so long. I'm sorry that we didn't have time to cover all this in class. Obviously, it's a lot of information, but please do remember to do the practical exercise handout that I gave you. That's not graded, but it will help you to better understand and kind of recap everything that we talked about. But do make sure that you turn in your quiz that is graded, but hopefully you guys shouldn't have any problems with this. If you do have any problems with this, please do not hesitate to come by. I will gladly have some one-on-one time with you and go over any details that you might be a little foggy on, or if you need any greater explanation of some of these different methods. But this should give you guys a pretty good knowledge level to help you out when it comes time to breaking out a military map and having to plot your points and figure out where you're going and where you are. All right, so thanks again. Have a good night. See you at lab.